Hi physics, today we're going to talk about superposition and interference. Okay, so a property of waves is that more than one can occupy the same space. When that happens, we call it interference. And the way they combine is via superposition, which is really simple. I'm going to show you what that looks like. So as two wave pulses approach, they have different amplitudes, A1 and A2. They occupy the same space, okay? And the new amplitude is just the sum of their original amplitudes. So if this was a meter and this was half a meter, the new wave would be 1.5 meters of amplitude. Okay. Then they pass through each other unchanged. So that's why you can talk to each other in a crowded room. The sound waves can travel through each other. And they superimpose. If you're in the middle of a conversation between a bunch of people, you may not be able to hear it. But they pass through each other unchanged, so the person it's intended to can hear what the other person is saying. I hope you've experienced that. Now, if you see a crest and a trough, so one's up, one's down, the result is a smaller amplitude. Okay, so you just subtract them, and that's called destructive interference. All right, when two crests form, that's called constructive interference. I think I wrote it down, but didn't mention it. Okay, so constructive interference, you get a larger amplitude wave. Destructive interference, you get a smaller amplitude wave. As before, these waves just continue on unchanged after interference. All right, now I want to talk about what happens when two wave trains, so just like a bunch of crests and troughs, not just pulses, pass through each other. The result is a wave that alternates between constructive and destructive interference. And I'll try to convince you of that. I'm going to link to a demonstration video. So we can achieve this by just generating a wave. Say this is a spring. It's attached to a wall. Remember that crests are reflected as troughs. So what I really want to point out is I drew this spring, the distance from, say this is a person maybe holding the spring, okay? It's two wavelengths. And that's special because what you're going to see is it hits the wall here and reflects like this. So the red reflected wave travels that way, the blue wave is traveling this way, and these waves are passing through each other. Okay, so I got red and blue, they're going like this. All right, where they occupy the same space, there'll be interference, and you superimpose, you add their amplitudes, their displacements. You see where they intersect? It's right in the middle. So it's the displacement is 0 at all those points. That means the displacement of the combined wave is 0. Everywhere else, as the waves move through, it's going to pass. Everywhere else the waves pass through, it's going to go from high to low. It's going to oscillate between up and down. But where I've drawn these intersections, those points aren't going to move. You call those nodes. You're going to see it more clearly in the video I've linked. All right. If you produce a wave of particular wavelength, that's like a multiple of the distance to the wall it's reflecting from, you can produce something called a standing wave, which you will see in the linked video.